Today we are going to learn about mastering ROC curves in model evaluation. You will gain skills in constructing, interpreting, and applying ROC curves effectively in your machine learning projects. Welcome to our video on mastering ROC curves in model evaluation. ROC curves, or receiver operating characteristic curves, are a fundamental tool in evaluating the performance of binary classification models. They help us understand the balance between true positive rates, TPR, and false positive rates, FPR, which is crucial for making informed decisions in model deployment. In the next 15 minutes, you'll learn how to construct, interpret, and apply ROC curves effectively in your machine learning projects. Let's dive in. To fully grasp ROC curves, we must first understand two essential metrics: the true positive rate, TPR, and the false positive rate, FPR. The true positive rate, also known as sensitivity or recall, measures the proportion of actual positives that are correctly identified by the model. It is calculated as the number of true positives divided by the sum of true positives and false negatives. On the other hand, the false positive rate is the proportion of actual negatives that are incorrectly classified as positives. It's calculated as the number of false positives divided by the sum of false positives and true negatives. Both these rates are crucial as they determine the trade-off between sensitivity and specificity in a model. A high TPR with a low FPR indicates a robust model. Understanding these metrics is key to interpreting ROC curves and making informed decisions about model performance. A ROC curve is a graphical representation of a model's performance across different threshold settings. To plot a ROC curve, you start by calculating the TPR and FPR for various threshold values. On the graph, the x-axis represents the FPR, while the y-axis represents the TPR. Each point on the curve represents a different threshold value. The diagonal line from the bottom left to the top right corner of the plot signifies a no-skill classifier, meaning random guessing. Ideally, a model's ROC curve will bow towards the top left corner, indicating a high TPR and a low FPR. The steeper the curve, the better the model's performance. For plotting, tools like Python's scikit-learn library or R's proc package are highly recommended, as they provide built-in functions to automate this process. The area under the curve, AUC, is a single scalar value that summarizes the performance of a model across all possible classification thresholds. The AUC ranges from 0 to 1, where an AUC of 0.5 signifies a model with no discrimination ability, equivalent to random guessing. An AUC of 1 indicates a perfect model with 0 false positives and false negatives. A higher AUC value is generally better, as it indicates that the model has a good measure of separability. The AUC is particularly useful for comparing multiple models, as it provides a single metric to assess overall performance. It's important to remember that while AUC is a valuable indicator, it should not be the sole criterion for model selection, as it does not account for the cost of false positives and false negatives. When evaluating multiple classification models, ROC curves offer a visual and quantitative method for comparison. By plotting the ROC curves of different models on the same graph, we can compare their performance directly. Models whose ROC curves are closer to the top left corner are generally better. However, the curves may overlap, making visual comparison challenging. This is where the AUC becomes invaluable. By comparing the AUC values, we can quantitatively assess which model performs better across all thresholds. While a higher AUC is preferred, it's crucial to consider other factors such as model complexity, interpretability, and the specific costs of false positives and negatives in the context of the problem domain. This comprehensive approach ensures you choose the right model for your specific needs.
While ROC curves are powerful tools, they come with their own set of challenges and limitations. One common pitfall is the misinterpretation of the curve shape without considering the context of the problem. Class imbalance can also significantly impact the ROC curve, as a model may appear to perform well despite being biased towards the majority class. Additionally, an over-reliance on AUC can be misleading, especially if the costs of false positives and false negatives are not equal in the application domain. In such cases, precision recall curves may provide more insight. It's crucial to consider the specific requirements of your project and not just rely on ROC analysis alone. By being aware of these pitfalls, you can use ROC curves more effectively and make more informed decisions.
ROC curves are widely used across various industries to evaluate and improve model performance. In healthcare, ROC curves help assess diagnostic tests, balancing sensitivity and specificity to ensure accurate disease detection. In fraud detection, ROC analysis aids in identifying transactions that are likely to be fraudulent, optimizing the balance between catching fraudsters and minimizing false alarms. In marketing, ROC curves are used to segment customers based on their likelihood of responding to campaigns, allowing for targeted marketing efforts. Credit scoring models also leverage ROC curves to balance the risk of approving high-risk applicants against missing out on potential customers. These real-world applications highlight the versatility of ROC curves in improving decision-making and model deployment. By studying these examples, we can gain valuable insights into the practical use of ROC analysis.
Generating ROC curves has been greatly simplified by the availability of robust tools and libraries. In Python, the scikit-learn library is a popular choice, offering built-in functions to calculate and plot ROC curves with ease. It provides flexibility and customization options to suit different project needs. For our users, the proc package is widely used, providing comprehensive features for ROC analysis. Both libraries automate the process of calculating TPR and FPR across thresholds and plotting the resulting curve. When choosing a tool, consider factors such as ease of integration with your existing workflow, compatibility with your data, and the specific features required for your analysis. By leveraging these tools, you can efficiently generate ROC curves and focus on interpreting the results to make informed decisions about your models. As we conclude, let's recap the key takeaways from this video. We've explored the fundamentals of ROC curves, learned how to interpret true positive and false positive rates, and discussed how to plot and analyze ROC curves effectively. Understanding the area under the curve, AUC, is crucial for comparing models, but remember to be mindful of the common pitfalls and limitations of ROC analysis. With this knowledge, you're now equipped to apply ROC curves in your machine learning projects, enhancing your model evaluation and decision-making processes. Thank you for joining us, and we hope you feel confident in mastering ROC curves for optimal model evaluation.